All right, so good morning, everyone. So today, I I think it's going to be a really exciting activity we're going to be doing. So we're going to be talking about iteration, which is something that I think the more complex data sets you have, the better fit you're going to find for this type of activity. And so I sent you all an email earlier this morning asking for you to create a new project on your GitHub first, called 08 iteration. And then and I uploaded some files, both a data set and also a script to 2025 DSA. So I asked you to set that up on your side. If you have done that successfully, then you should have on the folder of this class here, you should have now a 08 iteration under which you have a code, data, and output. You have that RStudio project coming through the GitHub. When you create a new project through using version control, it creates that project for you already. And so you should have the script 0311 iteration partial under the code folder, and then the data set nematode_rs on your data folder. If you're still doing this, catching up, I'm just gonna give you a quick moment to do that while I tell you a little bit about our overall game plan from this point on. So I am grading your midterms, and we have one student that is going to need to make up for that exam. And so we'll only be releasing your grades after that student takes that exam. And then we can talk more about that when that happens, which I think is going to be in just over a week right now. So next week, we're probably Thursday of next week, we're probably going to have your grades posted and feedback from my side as well. I almost finished this morning before heading to class, but I need just a few more minutes to finish a extra credit assignment for repeated measure. So if that's something that you're interested in, I'm going to be providing you the videos and the partial code for you to follow along. And then it's going to be a assignment related to that as well. Besides that, we're basically leaving behind experimental data analysis and getting started more with data science/machine learning topics. So today's topic is going to be very data science related. It's not machine learning or experimental design. It's something that you can apply to any data set basically, which is going to be on the topic of iteration. So from this point on, the goal here is going to be to expose you to this topic first, and then we're going to start talking about some algorithms in machine learning. We're also going to be seeing or exploring some open source databases for soil, weather, field elevation, and things like that. That for those of you that do work in open field agriculture can be very useful to be aware of and know how to manipulate these data sets. For those of you that don't, at least the open source side of it, it's not going to be useful, but still how we wrangle and extract information and summarize information from that is still going to be quite relevant to everyone. All right, so I am assuming that everyone was able to successfully create your folder structure for today's exercise. And so starting from that point, I'm just going to launch here my RStudio project. If you don't have that launch yet, please go ahead and do launch it. And then just launching my partial code as well. All right, so I guess just overall, has anyone ever done any iteration methods or approaches with your data in the past? Okay, so Shay has. Can you share with us what you've done?
Yeah, so like in a lot of my research, I have to iterate over like profile data. So
Mhm.
like different soil profiles might have separate data sets that are in a list, and then I use like lapply a lot to iterate over
Okay,
that. So
nice.
an example.
Awesome. So Shay here was saying that he uses lapply to iterate over soil profile data. That's it's so I'm good. What I'm going to be showing here, we're not going to be using the apply family of functions in R for a specific reason, but they're very useful as well. And if you once you learn them, I think it's really useful. When I was learning how to do iteration in R, I tried learning the apply family of functions, and it just seemed like they were not very consistent in the way that you use them. And so I found other ways, like a tidyverse way of doing that, which is going to be more consistent and I think like simpler to understand what's going on. But definitely, but I guess it's just two different approaches, but they as long as you figure out something that works for you, that's what matters, right? So I'm going to be teaching perhaps a different way than what you've done, but both of them are valid, both of them are useful. Awesome, thanks. Anyone else has experience with iteration in R or maybe,
Yeah, I
yes,
did some work for my remote sensing data.
remote sensing data?
Yeah.
Nice, perfect. Yeah, so this example we're going to be looking at today is actually coming from a remote sensing example. Uh, but again, what I really, if this is not something that you can directly relate to, what I want you to get from this is just the overall skill, which is applicable to any type of data set. All right, so today's objectives are going to be to understand the need for iteration and automation. And then we're going to explore three different approaches in R of how we can do iteration and automation. So we're starting very simple with just function writing. So if you are doing the same thing over and over again, you may decide to write a function for that, which may save you a lot of code. Um, and we're going to do something simple here in R, but really the concept is that if you have something that you're doing in across many data sets, let's say you're creating a ggplot of, I don't know, the box plot of some variable, and you always do that, and you always want your colors to be a certain way, your theme to be a certain way, your axis to have a certain style, then you can create a function that you just give a data set and this spills out that ggplot for you. So this is just one quick example. It's not what we're going to be writing for today, but it's one example where you can start writing functions. And my goal is for you to realize that writing functions is really simple and perhaps is one of the first steps for you to, start developing things on your own. And perhaps at some point you develop enough functions for what you do that you may want to decide to publish a package in R, right? So a lot of people do that type of thing. So we're going to start it off with writing functions. Then we're going to talk a little bit about loops in R, what they are, when we use them, how we specify them. And then finally, we're going to use list mapping functions, which right now, if you've never heard of this, it probably is not making a lot of sense in your head, but it's just another way of doing loops, but then using some functions from the tidyverse. All right, so the data set that we're going to be using on this exercise here is a data set on a paper that I co-authored in 2022. The title of the paper is Identifying Nematode Damage on Soybean Through Remote Sensing and Machine Learning Techniques. I left you the link of the paper there if you're interested in checking that out. But basically, just to describe to you the study, the data set, and so you can understand what is the challenge we have here is the study evaluated the potential of predicting nematode counts using drone-based remote sensing metrics in soybeans. If you're not familiar with it, nematode is a organism that lives in the soil that basically feeds on plant roots and therefore it can have a negative impact on plant growth, development, and finally yield. So it's something that if you can identify where and also imagine they're kind of like very tiny earthworms. Kind of think about that. If you've never seen a nematode, don't know what that is. But basically, it's a very, very tiny organism that punctures plant roots, feeds on roots, and therefore decreases the chances of those plants to grow and produce yield. And they are really not very mobile. So they happen in patches on the field. And even though that patch may increase over time, so like from this year to next year to 5 years down the road, maybe those patches are increasing over time, but they're really not mobile. They don't really move in the soil to a very large extent. So if you can identify patches where you have this happening on your field, you can perhaps use this information in the next growing season, perhaps to apply a product to try to control, or maybe plant different varieties that are tolerant to nematode attack. So basically, this was a field, a soybean field. So it was an open field here where soybeans were being grown. And then each one of those points you see there, the way that this happened was people went out to this field, and at each one of those points, they collected soil samples and also plant samples, especially plant root samples. And then they sent both the soil and the roots for lab analysis to count the number of different nematode organisms in those samples. But that's basically what this study did. And then at the same time when they pulled soil and plant samples, they also flew a drone with a multispectral sensor over this area. If you're not familiar with multispectral sensors, these are basically sensors we use in agriculture to keep track of crop health. Maybe overall, that's a good description if you're not familiar with it. So imagine we're trying to see how is the health of the crop on this field, and then connect that health or lack of it to how many nematode counts we had in soil and roots in each one of these points. That's basically what this study was trying to do. So if you're familiar with nematoid, then maybe this makes more sense. If you're not, then don't worry. You just need to know there were 3 different types of nematode species that were analyzed for. So Meloidogeny incognita, Pretilencus brachyurus, and Herodera glycines. So these were the 3 different species of nematode that were tested in these soil and plant samples. And this is, I'm just giving you here the acronym, which is what you're going to see on the data set. So Meloidogeny is MEL, Pretilencus is PB, Herodera is HET. That's what you're going to be seeing on the data set. And then again, on the same day that those samples were collected, a drone with a multispectral sensor was flown over this field. If you're not familiar with drone imagery or multispectral imagery in general, it basically gives you information in different bands. I'm trying to think of like an easy way to explain if you're not from ag. But basically think that, so each one of these bands represent a different part of the electromagnetic spectrum. And at least when we use them with plants, each one of them relates to different plant characteristics. So we have the bands of red, green, and blue, which are the ones that we call the visible bands, the bands on the visible part of the spectrum, which are basically what our eyes also see. We see bands our eyes can differentiate radiation in the spectrum that we call red, green, and blue. Normally, healthy plants absorb a lot of this radiation on these bands because they're using that for photosynthesis. So healthy plants absorb more of red, green, and blue, and therefore reflect less. Sorry, this could be a whole remote sensing class just on these topics. So I'm trying to be very brief, but still give you enough information to understand. And then near infrared is another part of the spectrum that also relates to plants, but in a different way. So while a healthy plant will absorb a lot of red, green, and blue, a healthy plant will not absorb, it will reflect a lot of near infrared. So near infrared has to do with the amount of biomass that the plant on the field has, and also the integrity of that biomass. So if a plant is healthy, vigorous, dark green, very healthy, is going to reflect a lot of near infrared. And if it is, again, a healthy plant, dark green, it will reflect very little of red, green, and blue. So taking one step back and just saying this maybe a different way, healthy plants will reflect very little of red, green, and blue because they are absorbing a lot and therefore reflecting little because they're absorbing that to run photosynthesis. That's what plants use to do photosynthesis, to basically create carbohydrates and then redistribute those within the plants and grow and create yield and so on. On the near infrared, healthy plants will reflect a lot of it because it's related to the amount of biomass and the integrity of that biomass. So a healthy plant that's not being attacked by insects or diseases, and it has all the nutrients, it has water, is going to have healthy biomass and reflect a lot in the near infrared. So we use these different bands that represent different information about plant canopies to then combine them into numbers and try to understand how healthy a plant is just by looking at an image rather than actually going to the field and collecting samples, which we still did in this study, but that's how these remote sensing techniques are used. And then red edge is just another band that's going to be related to plant health as well. So we're going to be using these 5 bands here from the multispectral sensor that we had. And the sensor itself gives you the reflectance on each one of these bands. We will also combine these bands in vegetation indices. So if you're not familiar with this, a vegetation index is basically just a formula that combines 2 or more bands into one number that helps us understand a little bit better plant health. So if you're not if you have never heard of this, if this is something new to you, perhaps my brief intro is not enough. But at the same time, I would imagine that those of you working with crops have maybe heard of or even used some of these technologies before that you can relate. So if this does not make sense to any of you, let me know after class. I'll be glad to expand and provide some resources if you need to understand what this is. All right. So the task that we have here, the goal that we have here is going to be to calculate different vegetation indices using those bands. So remember that vegetation indices are just formulas that combine 2 or more bands into one number and that are more easily related to plant health as is rather than using just the bands by themselves. And then for each of the nematode variables that were sampled and analyzed both in soil and plant, I want to run a simple linear regression against all possible combinations between nematode analyzed variables, so like the concentration or actually number of nematodes in soil and plants, different species, with each one of the remote sensing variables that we have, and run all possible correlations there. So for example, if one of the models that we are going to run is going to be the number of the myeloidogeny incognita nematode in the roots, explained as a function of reflectance on the green band. This is one model we're going to be running, a very simple linear model. However, what I want us to realize is we have 10 nematode-related response variables, which are going to be different species, if it's in soil or in the plant. And then we have 5 bands plus 10 vegetation indices we're going to be calculating as explanatory variables. So we have a total of 150 models we're going to be running. Now, imagine if you have to do all this by hand. You're going to basically have at least 150 chunks, each one of them changing either your Y variable or your X variable or both 150 times. Imagine you have to do this by hand. The nightmare it is in your head, the headache you get just from having to think of, okay, I have to change now this variable for that and this for that and do that 150 times. Making sure you keep track of each one of them, make sure you don't make any errors. And 150 models, it's even not that bad. I mean, some of the analysis we do in our team, sometimes we run thousands of models, right? So the goal here is just for you to understand that anytime you have a task, that there is like a framework of that task where you have to apply something, the same analysis or the same code, just to different subsets of a data or different versions of a data. That's when you need iteration, right? That's when you set up what you have to do and you just change the data set coming in to be receiving that operation that you set up. But that's basically what iteration is going to help us to do here, is doing that in an automated easier way that we don't have to type 150 times different models and change by hand what is the y variable, what's the x variable. All right, so I guess before we start coding, any questions about that, or maybe any thoughts that anyone would like to share? All right, so let's get coding. So we're just going to use a few packages here, so not a lot. And if you know these already, you've seen these before. I don't know if we're going to actually need an LRAA here in this exercise. Maybe this is just left over from a previous exercise. So for now, don't worry, just load the ones below. Don't have to install that. And then, as always, the first thing we're going to do is bring in our data set. So if you move the data set to your data folder, let's use a read CSV because it is a CSV file. And // go inside of data, and then you should have that nematode rs.csv. If you run that, and then we printed. So this is basically what we have. If we just take a quick look here. So 43 rows and 18 columns. We have, so this is data from just a single site. On the paper we did for 2 sites, but I'm just bringing 1 site here. So we have sample ID, which is basically just an ID of the sample in this field. And we have 45 samples, where each one of these rows here is 1 point on this map that were collected. And then, so we have here, just to remind you, so MEL is the short version of myeloidogeny, PB is Pretolenchus, and HED is for get a reminder of the name, Heterodera. So these are the different species of nematodes that the samples were analyzed for. And S stands for soil, so this would be the myeloidogeny in the soil, and then R is in the root. So I guess let me just show you here. So we have the 3 nematodes in the soil, and then we have the sum of all of them in the soil. So this is a count, is the number of nematodes that were counted within those samples. So we have each one of the 3 species by themselves in the soil, and then the sum of all 3 in the soil. We have the same way the 3 species in the roots. So R stands for roots, and then the sum of all of them in the roots. And then we have the sum of them total. So both in soil and in roots. And then we also have the number of eggs of those nematodes in the roots. And these are basically all of our response variables. These are our Y variables, is what we're trying to predict using remote sensing. We have yield as well of those points that were sampled. And then we start with the remote sensing data. So B is for blue, G is for green, NIR is near infrared, R is for red, and RE is red edge. So all of these remote sensing information are is basically a reflectance, and this is in a ratio that goes from 0 to 1. So for example, if we take the first sample here, it has a reflectance of about 4%, 4.8% in blue. It has a reflectance of about similar 0.48 in green. It has a reflectance of 44% on the infrared, of 3.6% in red, and of almost 15% in red edge. So this is just how much sunlight gets to the plant. This is how much of that total sunlight is being reflected back to the atmosphere, which is what the sensor is measuring flying on the drone above the canopy. So that's just the numbers. All right, so I think this was a quick rundown on our data set. And I guess, especially if you're not familiar with open field studies or maybe with remote sensing, is there anything I can help to clarify to help you all understand? Yes, Jonathan.
So do you want ideally more reflectance or less?
It depends, right? So what we're trying to do is to use remote sensing and try to see if we can actually relate nematode attack with remote sensing or nematode damage and remote sensing data. So for example, if you have an area of the field that has a lot of nematode from the samples that were analyzed, you would expect to have less crop health on those spots as compared to a spot that has fewer nematode counts. And then crop health is an overall term, but if we put that into terms of remote sensing, so as I was telling you, a healthy plant is going to be reflecting very little on the visible bands and reflecting a lot on the near infrared band. So that's what a healthy plant should look like, relatively speaking, to an unhealthy plant, right? So that's basically what we're trying to see here is, if we know these spots, we know how many nematode counts were there. We would imagine that the higher the nematode counts are, the less healthy plants will be in those spots. And we're trying to see if that's actually true, and if there is any specific combination of remote sensing data that has a better correlation with that, with the nematode counts themselves. Awesome. Any other? Yes, Comfort.
Yeah, I just wanted to ask that is it normal for the reflectance for the blue and green band to always be exactly the same?
So they're normally not the same, like exactly like this. It's actually a good point that I did not.
I think everything in the rows actually, maybe not everything, but it seems like.
That's true. That's a good point. I mean, a lot of them are the same as you're pointing out. Yeah, I'm not sure. Maybe I made some mistake when I was subsetting this data set, but that's a good point. They're normally not the same, right? So especially if we think about it, so all these three bands on the visible spectrum, they are absorbed mostly by plants to run photosynthesis. But the green band is absorbed just a little bit less, or in other words, it is reflected just a little bit more than than blue and red, and that's why we see plants as green. So yeah, normally the reflectance on the green would be a little bit higher than the blue and red, but yeah, that's a good point. I'm not sure what's going on here, but they should not be the same. Yeah, thanks for asking. Yes, Swabir.
Yeah, so I know for I mean drone you only take data by taking like images. So how do we come out with these numbers? How do
Okay.
we do?
Great. That's a great question. All right. So just giving you a little bit more background on how we ended up with this table, basically, right? So we flew this field here with the drone, and then we get basically one image for each band of this field. So imagine you would have a whole image just like we're seeing here, but for each different band of this field. So we're gonna have one image for blue, one for green, one for red, one for infrared, one for red edge. Then that image is orthorectified, meaning that we know where that image is in space. So we know where it is. And we also know where we sample these points because we use a GPS to take the coordinate to when we're sampling those points. So both the points and the image are co-located in space, right? So two layers co-located. So we basically just extract the pixel values around each one of those points on the images. That's how we end up with a table like this. I'm not showing you that because this is not an imagery processing class, but that's basically what was done. Yeah, awesome. Any other questions before we start coding more? All right. So as always do EDA, exploratory data analysis. Let's check here our summary just to take a look at it. So I guess very quickly, here we're just, all these nematode related variables are the count, right? So how many nematodes or eggs of those nematodes were present. So, I guess something that's interesting to see is maybe that we have a very high value here for Heterodera in the soil. All the other maximums are lower, way lower than that. In the roots, we seem to have a higher maximum count as related to the soil, right? So R stands for roots. We see that the maximum is really way higher than what we're seeing in the soil. So a lot more nematodes in the roots rather than just in the soil around those roots. We also have a good amount of eggs in the roots. So you would, as these nematodes are feeding on plants, they're also growing, developing, and reproducing. So we see eggs there. Here on the summary of the bins, yeah, actually the summary of blue and green are exactly the same. So maybe I made a mistake here. Thanks, Comfort, for bringing that up. But basically we see here, at least with the data we have, that the blue and the green band are ranging from between 4.3 to 5.4% reflectance. So again, the reflectance, you can kind of think of that as one of the pathways that light has once it interacts with plants. So the plants either absorb it so they can run photosynthesis, or they reflect back to the atmosphere, or they transmit through and just goes to the next layer. So here we're looking at reflectance. And again, we know that plants absorb a lot of blue, green, and red for photosynthesis, meaning that they reflect very little of it. So only about 4 to 5% of the total light getting to the plants, at least on these ones that we measure, were being reflected back to the atmosphere, which is what the sensor is measuring. On the infrared, you can see that's reflecting from 36 to 57% of the near infrared radiation that gets to the plant. And higher values here are better. That means there's more biomass, and that biomass is more intact or healthier. On the red here, we see from 2 to about 4% reflectance. So normally, again, plants will reflect a little bit less on blue and red and a little bit more on green. And that's the reason why our eyes perceive plants as green, even though they're still absorbing a lot of the green, but in relation to blue and red, they absorb a little bit less green and therefore reflect a little bit more. And thus we see plants as green. And then red edge is another band here that is ranging from 13 to 17% reflectance. All right, so let's do some density plots here. So what I want to do here, let me just kind of help you to develop the intuition. So what I want to do is basically have a density plot. So if you remember, density plot is just kind of like a histogram, but the outline of the histogram, we've done a lot of this already, but do a density plot for each one of all of our response variables, so the ones associated with the nematodes themselves, and our reflectance sensor information. So we want to do a density plot for each one of them, and we have 40 some columns, I guess. Or no, sorry, not 41. We have 40 some rows. So we have maybe, I guess, 15 columns that I want to have a density plot of. How do you think we can do that? Anyone has any thoughts? Okay, so Amandeep said use facet. Yes, we're gonna use facet for sure. That's a good one of the things we're gonna do here. However, let's say I want a density plot starting in melodogeny in the soil all the way to red edge. So for us to do facet, I need to have a column that I can say facet by this column. Right, so we don't have a single column that we can facet by. What do you think we need to do here? Group by? Yes, it's not going to be a group by, but it could be in other settings, like if we think of it. So we basically, let me give you a quick hint. We're going to have to reshape this data set. So right now it is in a wide format. Pivot longer, right? So we're going to use pivot longer here. So let's just start typing. If you add a pipe, we're gonna use pivot longer. And basically, so it has this argument for cols, where we specify which columns we want to pivot longer. We can just say, so mel underscore s as the starting one, use a colon, and then we just say re as our last one. So going from mel s all the way to re, I want to pivot longer all those columns. So if you run this, now we end up with 688 rows. And now we have a column that has all the previous column names under that. And the name of that column is name. And then we have a column called value, which is keeping all the previous values that we had before. So let me just show you again. So nematode, before we pivoted longer, it had 43 rows. We basically took 15 columns that were side by side. We took all their values and stacked them below each other all the way down. But now we have to have another new column that keeps the current column heading. So we know which values are associated with which variables. So when we do the pivot longer, if we take 43 times 15, that should be our, let's see, 645. Well, maybe we had 16 columns. Yeah, we had 16 columns that we pivoted longer. So that's why we end up with 688 rows after pivoting longer. So we took all those columns we wanted to pivot longer, took those values, put below each other, and then created a new column to give their names. Yes.
So when you do pivot longer, like how does it, what's the default for pivot longer and how it organizes all of the name? What's the default?
So Jonathan is asking, how does it organize the names? What's the default?
Looks like in this case by sample ID.
Yeah, I think that's what it's doing here is basically ordering by sample ID, but that order by itself is not really. I mean, it behind the scenes, it figures out which values go with which names, right? So we don't have to worry about that being wrong. But if you wanted to, let's say, oh, I wanted to see all the values where name is equal to Meloidogeny soil first. I mean, we could just come here and do an arrange based on name. If that would help you to visualize. So in this case, just arranging name alphabetically. So B was the first letter in that order. So we see here, so if we just keep track here, we have 45 sampling points. So the first 45 values here should all be B, right? Yep. But it keeps track behind the scenes, it keeps track, even though what it gives to you is not arranged or sorted by name, it does keep track of what is the site sample ID and then value that goes with that specific name. Yep. All right, so we have it now in a shape, I guess, that we can do a facet of some sort to do a plot. So then we can just feed this right into a ggplot. Let's call the AES right here. On the X, what would go on the X axis here? What do you think? So if you remember, just to give you a quick refresher, when we use geom density, which is what we're going to use for a density plot, the aesthetics that it takes is just the X variable or the X value, right? Because the Y is then calculated. It's going to be the density that geom density calculates for us. So we just give what variable, what column we want to go on the X axis. So which one of these do you think should go on the X? Value, right? Because that's where the actual values are. So value, let's add a plus. Let's call geom density here just to see, and let's just run before using a facet, just to kind of. So this is basically what it's doing for us. It's really not useful because it has the density plot for all those variables together. Some of them are in a decimal point, some of them are in a count range. So it really does not make sense to have all of them together. Then, as you already learned, we can just do a facet. So let's do a facet rep where I want to give a tilde and which column are we going to facet by? So let me just run the data set coming in so you can see the data set, what column do we facet by? Name, right? So let's facet by name. If we just run that, then we get one plot for each one of the names and then a density plot for each one of them. What's happening here is that the default value or the default behavior of facet wrap and facet grid is to keep your y-axis range fixed for all of your plots. And that's why we're not seeing any of them well, because they all have a fixed range of the density. And that makes no sense. So for us to allow facet wrap to have a different y-axis for each one of our facets, we come here, it has an argument that's called scales. We're going to say scales equals free. So it's going to allow these scales to change depending on the plots. And then now we can really see the distribution of those, of each one of those variables. All right, so a few things that we realize here. So I guess every time that we have a nematode related variable, we see that they are skewed, right? So they have a high frequency of low values and then a long tail, right? So every time we see that, so a high frequency of low values and then a longer tail, meaning that they have maybe some outliers here going on. Right, so we see that across basically all of the nematode variables. And everywhere you're seeing something more normal looking, that's probably a remote sensing variable. All right, so I think this was useful for us to create some understanding of the data distribution as well. I would anticipate we're going to have some challenges just from the data side as far as how well we're going to be able to predict nematode using remote sensing, given that they are distributed in this pattern. Okay, so the first step here that we're going to be talking about automation is going to be writing a function. So what I want to do here is that, as I was telling you earlier, there are vegetation indices, which are basically mathematical formulas that combine two or more bands into a number, into an index. And where the most common, most popular, maybe for sure the first one developed using at least satellite imagery is called normalized difference vegetation index. And the short version of that is NDVI. So if you ever hear about using imagery in agriculture to correlate with crop health, NDVI is probably something you're going to be seeing because it's the most popular one. It's not, so it was the first one developed, and because of that, it's the most popular, but it has some shortcomings. I'm not going to be talking too much about that here, but the goal is to show you that NDVI is one of them. There are hundreds of vegetation indices that have been developed since then. So just want to show you the most popular, so create the intuition, but knowing that this is not the only one and is not the best one that's developed for different purposes. But it's the most popular one. So what is NDVI? NDVI, basically you take the reflectance on the near infrared and you minus that from the reflectance of a band in the visible part of the spectrum. This band here on the original NDVI is the red. So the original NDVI is near infrared minus red divided by near infrared plus red. And this is our reflectance, which is the data we have, right? So reflectance on the near infrared minus reflectance on the red divided by reflectance on the near infrared plus reflectance on the red. Some variations of the NDVI is that instead of using the red band here on this where it says vis, I had that just to point out that is a band in the visible part of the spectrum. So the original NDVI, that band is the red band. However, there are some variations of the original NDVI where the formula is the same, the near infrared band is the same. All the changes is what visible band is used on the second slot here of the visible band. So again, using the red band is the original default NDVI, but we can use the green, we can use the blue, we can use other bands in the visible in this place here of the visible band. And the reason why I'm telling you all this is because we're going to be calculating NDVI using the original NDVI formula with the red band, but also with the other versions of it that use, instead of the red, uses the blue and then the green. So the overall formula that we're going to be looking for is this. And so I want to show you here one example of how we would create this index here, just to create the NDVI that uses the red band. So if you come here on this chunk, let's give it a pipe. So I want to create here, basically, I want to implement this formula in our code and create a column that's going to be for the NDVI using the red band as the visible band. So if we come here, let's do a mutate. I want to call this R NDVI, just to say that's the NDVI using the red band. And basically all we do is we just match this formula with our column names, right? So if we just print here nematode, and we go to the remote sensing part of the data set, our red band is the name of the column is R, our near infrared is NIR. So we basically just type the formula here. I want to open parentheses and just type NIR minus R divided by, open and close parentheses again, NIR plus R. If you run that, and then you inspect the last column, you basically calculated the red band based NDVI. So this number here ranges from -1 to 1, just to give you some idea. So -1 to 1, where values, so normally plant related NDVI is going to range from 0 to 1. If you have more soil or other surfaces, you may have negative values, but for our purposes, it's going to range from 0 to 1, where the higher this value is, the healthier the crop is. That's what we're trying to get here. So remember, and why do we use vegetation indices? So there are different reasons, but one that I think it's easier for us to just relate to. Remember that I told you that the more biomass, the more reflectance in the near infrared, and the darker green, so meaning that it's very healthy, very vigorous plants, then the less reflectance in the red we have. So the red relates to color, to pigmentation, and the near infrared relates to biomass, how much biomass there is out there. Both of those things are important for us to understand plant health, because you can have maybe a plant that was vigorous initially, but then run into a stress and then becomes a stress. So it may have biomass, but it may be very like yellow looking, so not very healthy. On the other hand, you can have a very small plant that is very dark green because it has all the nutrients it needs, but it just does not have a lot of biomass. So you have to combine both the pigmentation and the biomass together in a number that gives you a better idea of crop health. So that's why NDVI was developed, because it combines both of those bands and the information that they relate to plants into one number. All right, so this is basically how we would calculate NDVI. But we're going to be calculating different versions of NDVI. So we're going to use different bands on the, so we're going to change the red for the green and then for the blue. So we're not going to have just one NDVI. We're going to have 3, I guess, in total. So instead of us coming here and then copying and pasting this, so I'm going to do here, you don't have to, but if we were to do something like this, right? So type 3 times, and then just come here and change blue, and then change green, and then change the band here. We could do that by hand, but because it's the same overall formula, we're just changing what is the visible band going into it. So here would be the blue, and then the green, and so on. What I want to do is create a function that would just give what is the band on the visible and then the band near infrared, and that spits out to us an NDVI based on that specific visible band. That's our goal. So I'm just gonna delete this. And instead, we're going to create a function here that is going to help us to do this in an easier way. All right, so every time you use a function in R, it is defined in a similar way of how we're going to define this function. Of course, the more complex functions we use, they have more things behind the scene. This is just going to be a very simple function, and the name of this function is NDVI. So this is what I want to call this function. The way that R knows that this is a function and not just an object, so we give the assignment symbol and we call this function called named function. So this is how R knows that this is going to be a function and not just an object. Inside here of this call for a function is where we establish what are the arguments, what are the things that this function requires that we're going to be giving it for it to do something with it. So the two arguments I want to give here is, and I'm going to call them NIR, comma this, and basically what they're going to mean for this function is the argument, the first argument that we give it is going to be that NIR argument is the column that's going to have the near-infrared reflectance. The second argument is going to be called vis, and it's going to basically carry the values of any visible band that I wanted to calculate NDVI for us. Now, the way that we begin this function is open and closing curly brackets. I'm just going to hit return a few times just to give it some room here to code. And really, all we have to do here is just now type out the formula that we just did before, which if you look it up, is going to be open and close parentheses is NIR minus vis. And notice that I'm using NIR and vis here because those are the arguments I created on my function call. If I call this A and B, I would have called these A and B. I'm just calling them near-infrared and vis just so they are intuitive. But I just wanted you to understand these names we're using inside the function are related to the names that we gave to our arguments. So I'm just going to undo here. So near-infrared minus vis divided by near-infrared plus vis. That is our overall formula for NDVI. Now, if you run that, notice that you have on your environment here, you have a functions that basically now you have this NDVI name here showing up. So you basically have this function available for you to use in your environment. We have not used yet, we just created the function. And basically, we're gonna call this name NDVI. We're gonna give which column name has the near-infrared information, which column name has the visible information, and then the function is gonna do this calculation for us and return the result of that to us. That's what this function is basically doing. So let's see how that would compare using that function. How would that compare with our perhaps more manual process that we just did on the chunk above? So if we come here on the next chunk after we created the function, what I want to do here is give it a pipe. Let's call a mutate. I still want to call this column R NDVI because it's going to be the NDVI using the red band. And then now we just call that function. So it's going to basically, the function name is NDVI. Again, the first argument is the column name that has the near-infrared data, which in our case, if you look on Nematode, it is near-infrared, or it is NIR, right? That is the column name here. And then because I want to use the red as the visible band, I give the R as the second argument. So if we run that and you just look at the end, you basically get the same result as we did manually before. But now, instead of manually typing out the formula 1, 2, 3, 4 times that we may need, we have a function that does that for us. And all we have to change is just which bin is going to the visible position of the formula. All right, any questions about creating a function or how we're using things up until this point?
Okay.
Yes.
So we do need to type again and then to mutate or, so let's say we wanna do the blue one, so we just gonna bring NI and B. Then we have to take the MDPI.
Yeah, so Charles' question is, how are we gonna then, if we use a different visible bin, how is that gonna change, right? So that's gonna happen in the next chunk here, but basically, we're just gonna have to change this band and just give a new name to this new column, right? So we don't overwrite, but that's basically what we're gonna do. All right, so let's go ahead and calculate all the vegetation indices that we did on this paper, which included a few versions of NDVI. So I left you here. So if you come to the next chunk, I left you here the scaffolding of it. What I want you to do is after that nematode, add a pipe, and then you can come after the calculating NDVI based indices. And we're going to calculate 4 different NDVI. So if you give a mutate, the first one is going to be the same as we've done first, which is the R NDVI. So the NDVI that uses the red band. We're going to call the function NDVI that we just created. The near infrared band will always remain the same. The visible one's going to change. So for the red NDVI, our column name is R, right? So this is exactly what we did above here that created that vegetation index right there. But now I want to calculate 3 other versions of NDVI where instead of red, we have blue or green or red edge. The infrared remains the same, but the visible band is going to change for us. So you can either add a pipe and other mutate, or you can work inside of the same mutate here. So if you just come after, in between those 2 parentheses, add a comma, just break line a few times. The next one, I want to calculate the green NDVI, which is the NDVI that uses the green band. So G NDVI is going to be equals to the function that we created, NDVI. So let's see, what arguments should we add here? Usman, what do you think? NIR, all right. What about G, right? Yeah, so we have a column on the nematode data set, we have a column that's G that stands for the green band. Yeah, so that's exactly how we would do it. If you just want to go ahead and run it, and then we can inspect, because now we're assigning that to an object called nematode W. We can inspect nematode W to look into that. We're gonna have now the red NDVI and the green NDVI. All right, so let's do the same for the blue. So B NDVI is going to be equals to the formula or the function NDVI where we give NIR comma B, because that's now the blue one, even though in this data set seems like it's going to be the same as the green. And then lastly, I want to do the red edge NDVI. So let's call that RE NDVI. This is going to be equals to the NDVI function, and we call NIR, and we call the column RE. That's the one that has the red edge information. If you're familiar with remote sensing and crops, and you've used some of these before, the RE NDVI is basically what is called NDRE, or the normalized difference red edge. It's a very popular vegetation index as well, and it overcomes some of the limitations of the red NDVI. But that's the extent that I want to talk about here, because again, this is not a remote sensing class. All right, so if you run this and you print nematode W, you're going to have now all of your 4 versions of NDVI, each one of them using a different visible band, going from red, green, blue, and red edge. Okay, so this was basically a very simple implementation of a function. We're going to create another function here later in this exercise, so you're going to see that again. But really, the main thing for you to keep in mind is if you're creating a function of your own, you're going to have to call this function. And then in it, you give whatever arguments it requires. And then inside of the function, you're going to be relating back to those argument names, regardless of how your column is named. So your column could have been called, I don't know, x1, x2. Still, your function is going to be near infrared or NIR and vis. So if you remember, when we started talking about functions, remember they have arguments, right? So if you do type NDVI and you type tab, you're going to see the two arguments that we specify there. So one is near infrared, the other one is vis. Remember, we talked about arguments. You can even give if you want to give first the visible and then the near infrared, as long as you call out the argument name, you can do that. But if you're not calling argument name, you just have to give in the same order as the function was created. All right. So if you come back here to the nematode.w chunk, you can finally add a pipe after we calculated the NDVI based indices. And then you can just uncomment the mutate until the end. So what this is doing is each one of those lines of code are calculating a different vegetation index that takes a different mathematical formula. And really, my goal is not to show you to type out those formula. Each one of them is just to basically recreate what was all the indices that were used in the paper, which are these. If you want to know more about these indices, why we use them, how they're different, you can maybe go back to the paper and take a read of that. But again, these are just different indices, which are different ways of combining two or more bands into a single number. So if you remove all the comments and you just let it run and you print it, now we have 28 columns from the original 18 because we added all the vegetation index columns at this point. All right, any questions? So the next step here is going to be for us to, so we're going to write one more function and then start some iteration. I think this is a good point for us to take a quick 5-minute break. And then once we come back, we're going to keep developing this exercise here. So let me give you 5-minute break and then we'll be back. All right, so let's come back to our exercise. Okay, so the next thing I want to show you here is we're gonna create a function that's gonna be a little bit more involved than the previous one. So my goal here is for each one of these columns, each one of these variables that we calculated, and even the ones we had before coming in on the original data set, I want to calculate their mean and their coefficient of variation. If you remember, R does not have a function for CV. So when we calculated CV in the past, we first had to calculate the mean, then the standard deviation, and then use them to calculate the CV kind of by hand, sort of. So what I want to do here is create a function that we give it a column. So we give it a list of values. And this function is going to take that column, calculate the mean, the standard deviation, and the CV, and return back to us that information in just a single line for that whole column. So let's write a function here. I want to call that function mean CV because that's what we're going to get from it, is basically the mean and the CV. So because we're going to create a function here with the name mean CV, we need to use the function. So here inside of this function, we give it what is the argument name that we're going to be taking throughout this function that will be required for the user to provide. I want to call this X. It's a pretty standard argument for like an incoming data frame or a vector. So that's what I want to have here. If you open your curly brackets here, you can delete the closing one and just bring the closing one after the return, the data frame comment. So you have the opening and then the closing at the end instead of breaking line, because I do want you to keep these comments within the function for us to know what we're doing. All right, so let's say that we give this function a column that has values. And we want to calculate the mean, the standard deviation, and the CV. And we want this function to give us in the end the mean and the CV. That's what we're after here. I kind of laid out some of the steps that we're going to have to do in between. So the first one is going to be to calculate the mean and the SD. So how would you do that? So I want to give you just a scaffolding here of, I want to call this intermediary object as mean. So we're going to have an object called mean that we're basically going to calculate the mean of the incoming data set through this function. How would you code that? So we're not creating a new column because, so imagine if we give like 45 rows of values, I just want the mean. I just want one value. So we're not doing a mutate. We're just creating an object that's going to store the mean of this incoming column that we give it.
LS means
So ls means, I think that is not a function itself. So, and that would be a mean from a model, right? So we're not running a model here. So I think just let me help you all a little bit more. So we're going to use the function mean, right? Which is the simple function we've been using to get the mean of something. So the function is pretty simple. Sorry, maybe you were expecting something more complicated here. But I guess the part that I want you to think of is the mean of what? What goes inside of this function?
X.
X, right? The mean of X, because we named that argument as X. So it has to be a mean of X. If we remember, in case X, whatever X is, when we use this function, if that has any NA values in it, we have to use the argument na.rm equals true, just to make sure that that na value does not mess up our mean calculation. All right, so the next intermediary step here is to calculate the standard deviation. I want to call that SD. We have a function that is called SD as well from R. And here again, we're going to give X, right? Because again, I want the standard deviation of the column that I'm giving to this function, and the function is calling that as X, as we specified in the argument. And again, na.rm equals true. Okay, so once we have calculated the mean and the standard deviation, the CV is just a ratio of them times 100. So the CV, the coefficient of variation, which there is no R function for CV. There is an R function for mean, there is one for standard deviation. There is not an R function for CV. So this is basically, if you open and close parentheses, is just the SD divided by the mean times 100. This is what the CV is. So right now, this function calculates the mean and the standard deviation. It uses both of those calculated values to calculate then the coefficient of variation. And now what I want to do is, and this comes down to what do you want this function to return back to you? What I want it to return back to me is a data frame. So I'm going to create here an object that I want to call df, just for a simple data frame. Guess the assignment symbol. And then we're going to use the function data.frame to create a data frame that it has the mean and the CV. So the way that we create a data frame here is, so this first word mean is just the column name. And then I say equals to, and this second mean is that object that the function is creating. That is just how the data frame function works. Is the first name you give is the column name, and the second is something else. So that in this case is the same name because we're creating that object above. And then I will also want the CV. So CV is going to be equals to CV. And at this point, this function calculated or created four objects for us. For us to be explicit which one of them I want the function to return back to me. I don't want all of those objects. I just want the data frame in the end. We're just going to say df here. So whatever is the last thing that's printed is what it returns back to you. So if we run this, now you're going to see that you have this mean CV function on your environment. And I want to apply this to one of the columns first, so you see how, in a very simple example, how that would work. So if you come here on the next chunk, let's call this function, so mean CV, we just created that function. I want to give here one of the columns in our nematode data frame. So let's say nematode W, $, so we get one of the columns. Let's get the RNDVI column. Oops, I think I actually had a typo on my side. I had RDVI, but in yours, let me just fix that. Oh no, I have RNDVI. RDVI is something else. Yeah, there. So if you run this, what you get back is this simple data frame that has two columns and one row, where one of the columns is the mean of the column that you gave it. So in this case, all this nematode W RNDVI is equal to X for this function, right? That's the incoming vector. So if I just print nematode $ RNDVI, this is what you're giving the function. This is what the function is getting as X. And then it returns to you the mean and the coefficient of variation. So a very simple function. I mean, a little bit more complicated than the first one. And just for you, perhaps to help you understand, the first function here, it was already due. So we did not assign this to an object. You don't have to assign what you're doing to an object if that's the only thing the function is doing. But on our more complex example of mean CV, we're creating multiple things in between, and we don't want all them back. I just want the df back. So that's why on the NDVI function, we did not have to create an intermediary object. You could if you wanted to call this like, I don't know, result. And then just print result, it would be the same outcome, right? But here is, we're just controlling, so on MinCV, we're just controlling what I want back from this function because we had multiple intermediary steps. So that's why we created intermediary functions and objects as well. All right, so any questions about this function here? We're going to be using this function again. So you mean like if we just did this, like if we did not name it and just did that? I think it's going to return the data frame. Well, let's try it. That's the cool thing about coding, right? You can try, and if it doesn't work, you can fix it. But so Charles' question was, what if we just don't create that DF object and then we don't return it and just have this last thing as what's being returned? I think it would still work. So I'm just going to try that to test. Yeah, it still works. Yeah. Yeah, as long as the last thing that you want to return is that, then you can do that. So sometimes we're not going to be doing that in this exercise, but sometimes when I write functions, I may want 5 things back, for example. You know, so then you have to explicitly say that you want to return a list of these 5 objects. So every time, if you remember, every time you get a function output that has different components. So it has like a $sign. Remember like the random effect function that we use to calculate the residuals that gives you like the $sign wrap and $sign k rate in wrap. So it has those different components of $sign wrap, $sign k rate wrap. That would be an example where a function gives you more than one output back. And then you have to specify that differently. But if you just want one output, then it can be the last thing that you create in the function, and then you don't have to print that, I guess, or save to it an object. Yeah, awesome. All right. So now we're going to start talking about, so what we've done until now when it comes to automation, or it is more automation in this case, is if you're doing something that you're repeating a lot of times and all you're changing is the incoming data set, you can write a function for that. You can write a function that takes in that incoming data set, whatever is the variable you're changing, and then keeps everything else the same and returns you something in the end. Right. So another example here would be perhaps you create your own style of ggplots that you have a specific theme, specific colors you want to use, specific size of things, a specific font type, and all types of things you can customize on ggplots. You can create a function for, if you're always making, let's say, box plots, you can create a function that takes a data frame and takes a column that's going to be where your data is, or the columns you do want to use on your aesthetics, and just give that to that function. That function creates you a ggplot that is always consistent. So that would be another way that you could write a function. So now we're going to talk about loops. So loop is another level of complexity when it comes to doing iteration or automation using programming languages. So 2 of the most popular loops that at least I've come across are for loops and while loops. Specifically, I've used for loops every time I need to use a loop. A for loop is normally what I need. And so that's, I think, is the most common type of loop that you would need as well. So that's the one that we're going to be checking an example here. So basically, a for loop is going to iterate over an index value. And you understand what that means in a second here, through a data frame. So it's basically going to apply a set of functions to each, let's say each row, where row 1 is index 1, row 2 is index 2, row 3 is index 3, and so on. And you're applying the same set of functions or commands to each row in this case, and expecting something back. So that for loop is going, it takes the really important thing about understanding a for loop is understanding the index and how we use the index to say where the loop is in the entirety of that whole loop. So let's say if you're applying a loop on a whole data frame on row by row basis, and you have 45 rows, then the loop is gonna have 45 iterations until it gets to the end of it and stops. So the example that I want to give here is, let's say I wanted to calculate the mean and the CV for each of the response and explanatory variables of this data set. And we have a good number of them here. Because we're going to be implementing the same function, so mean CV across all of these columns, we can use a loop to do that for us. And I guess if you, let me see, I'm trying to not make things more complicated than needed with what I'm going to say. But if you have experience coding in Python, Python uses loops a lot more than in R. R has some ways of kind of hiding some loops behind the scenes for you, which I think is nice because you don't have to be doing loops all the time. But if you get more experience coding in Python, you're going to be doing a lot more loops, even for things that in R you don't need a loop for. In Python you will need. So loops are really important in programming in general. All right, so what I want to do here is for each one of the columns that we have a response variable like those from Nematode, or a remote sensing, or an explanatory variable like the remote sensing ones. I want to apply the function mean CV to each one of those columns. The function will return back the mean and the CV, and the loop will basically append those results to each one of those columns for us. All right. So again, what I want to do is extract the mean and the CV for each one of the columns in the data frame that we are interested in. So if you come here to the next chunk, I think I'm just printing this so we can look at the data frame itself. So we have a total of 28 rows, but really I don't want a mean of site. I don't want a mean of symbol ID. And that's it. So we're really starting on the third column and then all the way to the 28th column. I want to get the mean and the CV of each one of them. And we're going to do that using a loop. Okay, so one thing here that you see when you use loops, especially for loops and while loops, a lot of times you're going to have to create an empty data set that has the columns that you're hoping to get in the end, and it has just NAs running down. So you basically give the scaffold of what you want in the end, but non-populated, to the loop. So the loop goes in, calculates what you want, and then places those results in the first row of this empty data frame. And then it goes on the second column, calculates mean CV, populates on the second row, and just keeps doing that. I know it may be not very intuitive at this point, but basically just we have to create this empty data frame that then the loop will populate for us. So that's what we're going to do here next. So if you come here, let's create this data frame. So we're going to use the function data.frame. What I want you to picture is, in the end, what I want out of this is I want a data frame that has 3 columns. One column is going to be called variable, which is the variable name that I'm getting the mean and CV for. So variable, mean, and CV are the 3 columns that I want in the end. And so we're going to create those 3 columns right here. So variable is going to be the first one. Because we need to give an empty data frame, well, the way we're going to create an empty data frame that has already the dimensions of what the loop is going to work with is that we're going to use the function rep to basically repeat NA values 26 times. So if you just run this and you print it, this is what you get. A data frame with 1 column, 26 rows, and each one of the values here is just an NA. So and why 26, you may be wondering. Well, 26 is going to be the total number of columns that we're going to get a mean and a CV for, based on the nematode data frame. So all those nematode variables plus the remote sensing variables add up to 26. So the same way here, we're going to create a column called mean, and the same way we're going to say repeat NA 26 times, and we're going to have a column called CV that's going to wrap NA 26 times as well. So if you print that, now we basically have this empty data frame that has 3 columns, variable, mean, and CV, and it has all NAs. This is the empty canvas we're going to give to the loop, and we're going to say, go into that column, calculate mean and CV, and then populate this data frame here with the results. That's what we're going to ask it to do for us. So that's why we have to create this empty canvas to give it to populate. All right, I guess any questions here before we start with the loop? All right. So now let's go ahead and create a loop that again is going to go. So I'm just going to print here nematode W just to show you. So we basically starting on the 3rd column all the way to the last. I want to give this column to the mean CV function. I want to get the column name, the mean, and the CV for this column and populate that into this other data frame that we're given as the canvas. Once it does that for the MEL-S column, move to the next column. It does this, do the same thing, populate on the 2nd position of this data. So this first row is going to be for MEL-S. This second one is going to be for PBS, and so on. So we're basically taking a column, getting the name of the column, the mean, the CV, and then populating this other data frame. So not the same data frame, a second data frame, an empty canvas data frame that we're given it. All right. So to start a for loop, the way that R knows that you want to do a for loop is we use the word for, that's how it knows. And then we open and close parentheses like that. Here inside of this parentheses is where you establish how you want to call the index position of the loop. Every loop has an index position, and this is the key concept that differentiates a loop from other things. So normally in programming, unless you have a special reason to call this something else, you would call that index I. So I is going to be a position index that is going to make more sense in a little second here. So for I in, and then you give a sequence of numbers. What is the sequence of numbers? It's basically the sequence that you want I to iterate over. I know this can sound very confusing, but bear with me. I think in the end is all gonna click. So what I want to do, let me show you again, nematode W. Just gonna print ahead. You don't have to print if you don't want. I just want to print to show you. So what I want this for loop to do is to come starting on MEL-S. So not starting on, not doing for sites, not doing for simple ID, starting at MEL-S, getting that column name, getting the mean, getting the CV, and populating that in this data frame. So what I want to do here is the starting position of this index is basically going to be 3 because it's the 3rd position, the 3rd column on this data frame. If you wanted to calculate this for all columns, the starting point would have been 1. However, in our case, the starting point is going to be 3 because I want to start off on the 3rd column instead of the 1st. So we're starting on position 3, and then the column just gives you the range of values, right? So we're starting on position 3 and going all the way to the position of the last column. How can we know that? The position of the last column is basically the total number of columns of this data frame, right? If we just outside here, if I use the function encol of nematode W, this returns to me the total number of columns, which is 28. So I'm going to use this function here to determine what is the ending point of this index. So we're starting on position 3 and going all the way to the position 28, which is the total number of columns of the data set that I want to calculate the mean and CV of each one of the columns. So this is you starting your for loop by identifying how we were calling your index. We're calling our index I. This could have been A, B, C, X, whatever you want, as long as you keep that consistently naming it, whatever you call it first throughout the loop. I want to call I because that's the most traditional way of indexing in the for loop is to by I guess habit is to call that index I. So for I in starting on 3 all the way to 28, then do the following. So open and close curly brackets there, delete the closing curly brackets, and then add that closing curly bracket to the end. This is how we're gonna get started. So the first thing here is because in the end, I do want to know what is the column name that I'm getting the mean and CV of. I need to extract all the column names from this object that we are getting the mean and CV. So one thing I would just want to make clear to you, nematode W is where the data is, and this is where we're operating over, is nematode W. However, the results are not being saved on nematode W. The results are being saved on this empty object, nematode mean CV, that we're giving to the for loop. So keep in mind that we're calculating based on nematode W, but then saving the results to another data frame. Just keep that in mind as we're moving through here. So the first thing would be to get a list of all the column names on nematode W. I want to call this call names, this object. And there is a function called call names that we just give an object that we want the call names of. So we want the column names of nematode W. If I just run this and print call names again is just a list with the names of the columns of the object. All right. The next thing I want to do here is, if you remember, at the end of the first iteration of this loop, what I wanted to do is to go on nematode W, starting on position 3, which is mel S. I wanted to give me the name mel S. I wanted to give me the mean and the CV of that mel S column. That's what I wanted to give it to me and to populate that first row of nematode mean CV with. So meaning that I have to get those 3 pieces of information. So the next thing I want to do here is create an object that I want to call var name, which is basically the name of the column that the loop is working at that stage, at that iteration. So this is basically the object that we're creating above, call names. And then remember that we use the bracket notation to subset something. So if I wanted, so let's say I want to print call names here below, just so you see again. If I wanted, I don't remember, we're not doing for site, we're not doing for simple ID, we're starting with mel S. If I wanted this name here only, I could come to call names and use the index 3, right? Because that's the 3rd position on this vector. So if I say call names 3, it's going to give me just mel S. Now, here's where the index comes into play. I cannot put a 3 here because otherwise it's going to give me mel S every time the loop goes around. So I have to have a number that each time it goes around, it adds a +1. Goes around, +1. Goes around, +1. So this is where the I comes into play. So if I add an I here, the first time the loop goes around, I is going to be equals to 3 because that's the starting points that I'm setting on the loop here. So it goes around, it goes to the end of the loop. When it comes back on top, it's going to do the initial I, which was 3 plus 1. So the second time it runs, I is going to be equals to 4, and then 5, and then 6, and then 7, all the way until the ending point, which is 28. So that is the key difference of a loop, is you have an index value that adds 1 each time it reaches the end of it and restarts again. So if I do a var name call names I, the position that's going to be pulling out of call names is changing each time. You know what? I think we are probably going to take another 10 minutes to finish this loop. And we don't have all that time in class. So I think this is probably an okay point for us to stop here. Next class, we're going to pick up from here. So we'll remind you of what we're doing, and then we're going to keep developing this loop. And when it gets to the end of this loop, what you're going to see is this empty canvas that we're given it is going to be completely populated, where each row here with variable mean and CV is going to be the result of one iteration of the loop. So we're going to implement that next class. I think Arminder has opened the attendance on GitHub. So make sure you claim your attendance and make sure you save your project. And also, I think I've been forgetting to ask you this, but please remember on your side, if I forget to ask you, go on your Git, stage all the changes you made. And then let's commit. We can do here, I don't know, something, the commit message can be something like iteration part 1, commit, and then make sure you push it. So your changes are reflected on your own GitHub. All right, so once you staged, committed, and pushed, and also claim your attendance, then you're good to go. I'll see you on Thursday. We're going to finish this exercise. I'm going to introduce a couple of homeworks for you. One is extra credit, one is mandatory. All right. Any questions, I guess? If you need to go, go ahead and go. I'm going to hang around for a few minutes if anyone has any questions.